Hey, so y'all know the coding challenges series from the coding train, right? And I thought I would do something similar, but specific to Rust as a means of learning the language. So we're gonna make the Game of Life, developed by John Conway's. I'm assuming you already know what Conway's Game of Life is, but in case you don't, it's essentially kind of like a grid of cells like this that are either alive or dead. And each cell abides by a specific set of rules which lead to this complex looking behavior. And here are the rules here. Any live cell with fewer than 2 live neighbors dies. Any live cell with 2 or 3 live neighbors lives on to the next generation. Any live cell with more than 3 live neighbors dies. And any dead cell with exactly 3 live neighbors becomes a live cell. And this is all the rules. Just these 4 rules apply to every cell in the grid, leads to this complex behavior. And people have made crazy things with this, like clocks and computers and stuff. But yeah, let's get started. So we're gonna make a new Rust project. So for this project, and also for future coding challenges, we're going to use this library called MacroQuad. It says simple and easy to use graphics library, but it's basically like MacroQuad is to Rust, like P5.js is to JavaScript, or processing is to Java. It's like a simple all-in-one library for making sketches and simple projects. So we're going to import MacroQuad. And all MacroQuad projects essentially start like this. Use MacroQuad, prelude, everything. The main function is going to have a procedural macro, MacroQuad main, and we're going to call it life. Main can now be an async function. Here's the main loop. And there we go. Here's our simple, basic MacroQuad project. Here we import everything from the prelude module of MacroQuad. Prelude basically just means everything you're going to need, all in one package, basically. Next, we have a procedural macro on the main function. What this procedural macro allows us to do is to make the main function async. And this allows us to use nextFrame.await, specifically the await keyword. And what nextFrame.await does, it waits for the next frame. I know, shocking. This is in case our program is running faster than 60 FPS, is to wait until the next frame so we stay at 60 FPS. Or whatever we set it to. So we run this, cargo, run. Very nice. Here's our blank screen. So now we can get started on the actual project. Usually with these grid-based simulations, games, whatever, first thing we need to do is to define a grid. So const grid width, make this u size equals, for example, 10. and we're going to say scale of 32 equals, say, 30. So our playing field is going to be, or our grid is going to be 10 cells by 10 cells, where each cell is 30 pixels on our screen. So we're going to create a grid. Let grid. We're going to make this a slice of booleans in a one-dimensional array. So we're going to say false. And the size is going to be grid width times grid height. So this is a slice of booleans, where each boolean obviously represents whether a cell is alive or not. So here I have 100 falses, 100 cells that are dead. If you want, you could use another data structure, for example, a vector or a two-dimensional vector. I'm just choosing to use a one-dimensional list, just arbitrarily. Using a one-dimensional slice and one-dimensional list does mean we're going to have to make functions for converting between a 2D coordinates, a set of x and y's, to an index. So let's implement those. Fn pos to index x, usize. Usize returns a usize. Index to pos, index as usize will return a tuple of 2 usizes. So pos to index is usually the simpler one. It's just going to be y times the grid width plus the x. Index to pos is, so the x is going to be index modulo the width, I believe, and the height is going to be index divided by the grid width, and we floor this, but dividing two integers floors it automatically, so we don't need to do that. I think this is correct. Let's write some tests just to make sure. Test pos index conversion. And we're going to use super everything. Super just means everything from the parent module. So we were able to use these functions, pos to index, index to pos, and these constants. Seems to work. So next we should draw the grid. So for I in grid, you know what we can do? We can do grid.iter.enumerate. So this is a tuple with the index and the boolean representing whether it's alive, dot filter, I'll call it A, and return whether it's alive. So we actually don't need the index. So we're looping for every cell that is either alive or dead in the grid, enumerate it, so we also loop with its index, and filter only those that are alive. So we actually don't need this, because all cells that are going to yield from this iterator are going to be alive. So we only need their index. We say let x, y is equal to index to pos of I. We only need to draw live cells as like white rectangles, because dead cells we're going to draw as black, and the background is already black. So we won't need to draw those. Draw rectangle. X is x, y, the size is going to be scale, white. And we need to x as f32 times the scale, because these xy coordinates are in grid space, and we need to transform that into screen space, because each cell is 30 pixels on our screen. Or go run. And it should be the exact same as earlier, because, yeah, right now our grid is only of dead cells. So let's say for I in 0 to grid dot length, if gen range, generate a random number between 0 and 1 is less than 4. So we'll say 40% of cells should be alive. Grid I equals true. This should be mutable. Alright, here we go. We have a 10 by 10 grid where 40% of cells are alive and drawn as white squares. So now we can move on to the more exciting part, which is coding the actual simulation. So in our main loop, we say update, and we're going to make a function apply ruleset and apply ruleset is going to take our grid as a mutable reference slice of booleans, so what do we need to do? First, we need to loop over every cell, get its position, and then for each cell, count the number of live neighbors. So that means looping over each neighbor for each cell. So for I in 0 to grid dot length, let x, y equals index to position of I. Next, we need to count the neighbors. So I'm going to put this in its own function. Let live neighbor count as usize equals count live neighbors. Returns a usize. Actually, this can totally be a U8. So we will need, first of all, the grid. X as a usize, Y as a usize. And we're going to say for ry for relative y in -1 up to 1. And then for x, let neighbor x as usize neighbor x is equal to x plus rx. We're going to say x as I32. Neighbor x is going to be an I32. Going to do the same for y. So add the relative values, add the relative positions to the positions. Next, we're going to check the cell at that index. So we're going to say let index is pos2 index of neighbor x, neighbor y as usize. And the reason why I kept neighbor x and neighbor y as I32s and converted them back into usize here is because they can actually be negative. What if, say x is equal to 0. When we check the left cell, Rx is going to be -1. 0 plus -1 is, well, -1. If we keep this as a unsigned integer, this can actually cause problems because you can't subtract 1 from 0 with unsigned integers. So what we're going to do is check whether neighbor x and neighbor y are out of bounds. So if neighbor x is less than 0, or neighbor x is greater or equal than the grid width, continue. Out of bounds. Do the same with y. Actually, we can put this in the loop above, like this. Yep. So we get the index, and we say let is alive as a boolean is equal to grid at index. If is alive, neighbor count, or just count, plus equals 1. So let mute count u8 is equal to 0, return count. Alright, let me just inline this. If grid index is alive, count plus equals 1. Yep. So I just want to check that it works. Count alive neighbors, grid x, y. And then we're going to say print line cell at x, y has this many live neighbors. Just for debugging, I'm going to make the grid smaller, say 4 by 4. Yeah, I just want to let's just prevent this console spam by saying if is key pressed. Let's say if we press the space bar, we're going to step through the simulation. Key code, space, this. So let's see. So immediately we should see a problem. Cell 00 has 2 live neighbors, which is not correct. Let's say cell 1, 2, which is here, has 3 live neighbors, which is not correct. It has 2 live neighbors. So what we're seeing here is every live cell has 1 extra live neighbor it's counting. And that's because it's counting itself too. Let's say this cell here, cell 1, 2, I think it was. Yeah, 1, 2. When it's stepping through its neighbors, it's going -1, -1, -1, 0, 1, 0, and so forth. And it's going to come to 0, 0 and also count itself as alive. So what we need to do, let's go down here, and we're also going to check if neighbor X and neighbor Y are equal to 0. And now this should be correct. Oh, this should be Rx, Ry. Yep. This is correct. Alright, now that we can count the neighbors, next step is applying these rules. I'm just going to copy those. So we're going to say let is alive is going to be grid I. Any live cell with fewer than 2 live neighbors dies. So if is alive and live neighbor count is less than 2, die. Else if any live cell is alive with 2 or 3 live neighbors lives onto the next generation. So and is alive and live neighbor count is equal to 2, or live neighbor count is equal to 3, live onto the next generation. Else if any live cell with more than 3 live neighbors dies is alive and live neighbor count is greater than 3, die. And any dead cell, so not is alive, with exactly 3 live neighbors becomes a live cell. So live and neighbor count is equal to 3, live. So what we're going to do is, for cells that need to die, we're going to say grid I equals false. This one needs to live, so we're going to change this to a true. And this match arm here, actually, we don't need to do anything. The cell is already alive, and it's just going to continue to live onto the next generation. So we can just ignore this. Alright, let's run this. And we're going to get some weird results. So if we step through this, let's make it a little bit bigger. Let's say 30 by 30. We should get like a weird ripple effect. Yeah, here we go. You can see some weird lines forming in there, which is not really what we want. The reason why this happens is essentially because we're iterating the list while we modify it, or rather we modify it while we iterate. This is usually bad practice. In this case, it's going to make some cells interfere with the neighbor count of any subsequent cells. For example, let's say, I don't know, for example, this cell is going to die. Now this cell, which should have a live neighbor on its left, is now going to have a dead neighbor on its left. And it's going to create kind of like this ripple effect that's unpleasant to look at. So what we're going to do is we're going to have a separate list for updates that need to happen. Is a vec of a tuple containing the index as a usize and whether that cell should be alive or not as a boolean. Here we're going to say for cells that need to die, updates push index I false. And we just change this to a true for cells that need to come alive. So, update grid. For index and should be alive in updates dot iter. Actually, we can change this to a into iter because we can take ownership of the list. Grid at index equals should be alive. And here we go. This is the game of life. We're already getting these kinds of oscillating structures, I guess, oscillating patterns. And yeah. Alright, next. I'm just going to make the grid a little bit bigger. So what do we want to do from here? First, let's make it so we can start and stop the simulation with the spacebar. So it kind of runs on its own and we can pause it. So we're going to say let tick timer. Yeah. Make it a U8 equals 0. Say tick timer plus equals 1. And we're going to say, let's make it a constant. Const update rate U8 equals, let's say every 10 frames. Every 10 frames we want to apply the rule set. So if tick timer modulo update rate is equal to 0, apply the rule set. Oh, and tick timer needs to be mutable. So every 10 frames, we're going to apply the rule set. instead of having to press the spacebar, we're having it apply every frame. Neat. Oh, attempt to add with overflow. Yeah, of course. We need to reset tick timer. Tick timer equals 0. Alright, let's add pausing. Let mute is simulation paused as a boolean equals false. Every tick, so we're going to say tick, if not is simulation paused, apply the rule set. And we're still going to reset the tick timer to 0. And then right after we tick, we're going to say if is key pressed, key code space is simulation pause equals not is simulation pause. Pause, unpause, pause, unpause. Amazing. So, next and final thing I want to add is drawing. So when you press the left mouse button, it's going to draw live cells. And when you press the right mouse button, when you press the right mouse button, it's going to draw dead cells, or like kill whatever cell is hovered. So how should we do this? Let's make a function. Fn draw cell at mouse, draw cell at mouse. Take in the grid and live cell. This parameter is just going to be whether we're drawing live or dead cells. So we're going to get the mouse position first. Mouse X, mouse Y is equal to not mouse wheel. Mouse position. This is going to return a tuple of two F32s. So we're going to convert that into grid space. Let just X as a U size, is equal to mouse X divided by the scale. Dot floor, I believe. Actually, no, we're just converting it to a U size. And we're going to change the X to a Y. Okay. And we're going to get the index. Index is passed to index of X and Y. We of course also need to check whether this X and Y position is out of bounds. If X is greater or equal than grid width, or Y is greater or equal than grid height, return. And we're also going to check if the position is negative, just in case. If mouse X is less than 0, or mouse Y is less than 0, return. And we're going to say grid at index equals live cell. If is mouse button down, mouse button left, draw cell at mouse, we're going to reference the grid, and we're going to say draw live cells. If the right mouse button is pressed, draw dead cells. So pause, right mouse button, there we go. Cool, that works. I want to try to make a glider, or whatever it's called. So make some space. I think the pattern went something like this. Oh yeah! That's cool. So, this is it for this video. I encourage you to tinker around with this. For example, you can make it so when the simulation is paused, there's some text on the screen that says, hey, the simulation is paused. You can add a menu on the right for loading presets, or say you wanna add a glider without having to draw it every time. You can do that. From here, it's all up to you. I hope you learned something. See you next time.